signal of compatibility between the mention and the neighborhood of the entity. There is the compatibility of the entity with various types. How do I know the compatibility between entity and type? Now, like this. Here I don't. Here it clearly seems that I have type information. So that's the compatibility between type and neighborhood of the entity. That's the second leg of the triangle. And the third is this compatibility between the type and the mention. So footballers are mentioned with a typical text distribution. Mathematicians are mentioned with a different kind of text. That binds more to the type of the specific entity. So to repeat, the M to any affinity, the T to any affinity, and the M to LMT affinity. LM is language model. So when I refer to footballers, there's a certain language model or distribution from which I draw words. When I mention movie actors, I draw certain different distribution of words. So the reason why we might decide that these two mentions are of this one entity with the type is because these two green triangles are somehow better than if I try to draw in this red edges, which are words. So this is an extended graph model for what I was doing first, which was a two-stage process. Now it's closing the triangle and bringing in types into the game as well. Is this clear? So we call this type plus mention inference, or TMI, which is also short form for too much information. So how do we set this up? See, every mention has to 0 or 1 entity. So you have a dummy entity which is null as before. So each mention has to go to exactly 1 entity. To represent that, we turn this tripartite problem into a bipartite problem. So we have a node for every mention. That node has a variable which takes on values from entities. So M0 is one variable. EM0 is a variable. EM0 takes on values which are entity IDs. That's why it's called EM0. And for every entity that are candidates, I have a type and a node. So if E0 is a candidate for M0, there is a node called TE0, which takes on values of possible types for each. Similarly for E1. Here's the second mention M1, which might also refer to entity E1, therefore it connects to that same node. Or it may refer to entity E5 with its own set of possible types. So each node here can take various values. The green nodes take type values, the wine-colored nodes take entity values. And then I need the scoring functions. So what I basically said is the scoring or objective paradigm. And then we'll see how, we don't talk about algorithm again first. So this particular mention could be a mention of entities 0 or E1 or nothing. Every mention node has its own private nothing. There is no central nothing. All nothings are different. Similarly, M1 may refer to E5 or E1 or nothing. That's M1's nothing. And each of them has what's called a node potential or a local compatibility score, which captures the mention to the neighborhood of the entity. So if a particular mention talks about Michael Jordan, the statistics player, that's one score. The basketball player, another score. That's its proxy. That's one side of the game. On the other side, I need to find out the type of each entity. So now, every entity node has an entity node potential, which gives you a mapping from candidate types to their scores. And remember, that is figured out by looking at the entity graph, like previous. I look at the neighborhood of the entity. Looking at the neighborhood, and other entities in that neighborhood, I try to decide what the type of that entity might be. And I'm not sure. So for every candidate type, I build another score. Now comes the bridging edges, which is the links between keys and key variables. So this tries to capture the compatibility between the mention text and the type I assign to them. So if I chose a particular entity at the wine-colored node, and I picked a particular type at the green node, then I am satisfied to a certain extent. Why am I satisfied? If the mention has lots of words which have high probability of being mentioned for those types of. So there's a local compatibility of mentions and entities, local compatibility of entities and types, and then there's the cross compatibility between the mention and the type. Those are the edge potentials. The important thing is that if I'm looking at the node corresponding to E0, anything with a different entity has potential 0. So by the discrete gating apparatus, I turn the tripartite problem into a bipartite. Now, as I was saying before, every mention node also has its private null, and the private null entity also needs its type language mode. See, if I find no hint from a real entity, then the only hint of that what type that entity belongs to is from the mention alone. And for that, I need to erect certain placeholders. You can read the paper. That's a little technical. And then, for that dummy entity node, I don't have any bias. It could be any of the types in the world. So all the potentials are zeros or some uniform number. The only thing there comes from the mention itself. There's no, because that entity does not exist in my knowledge graph, I don't know what type it can. That's it. And there's an extension of those edge potentials to these fake nodes and edges. Now the summary is you set up this graphical model. It's a bipartite graphical model. Unfortunately, because of the structure of these potentials, there is no guarantee of optimality. You have to solve general integer programs to solve it. But there are these powerful message passing techniques in graphical model literature which you can use to locally optimize the assignment of types to the upper nodes and entities to the lower nodes. So the only missing piece here that I haven't quite explained yet is, given the network neighborhood of an entity, how do I start guessing its type? Here's an example. Suppose I want to recognize soccer players, or in fact, itself is ambiguity. Some catalogs will say football players, some catalogs will say soccer players. So here are some soccer players or football players. And in the previous graph, they are linked to various nodes. So one was dead giveaway. So Ronaldo is a football player. Ronaldo played in FIFA, won Golden Ball 12. But I told you, this is a very small world. Within a very short linked radius, all kinds of garbage types and other entities will come in. For example, that Beckham is a citizen of UK isn't a very good predictor of whether Beckham is a football player or not. So some of these edges, like the green ones, matter, whereas the other edges don't matter. The red edges are actually quite misleading. If I wanted to claim that Rooney is a football player because Beckham is a football player and they are both citizens of UK, that's meaningless. The only way I know that is by putting up negatives. So it turns out that Richard Branson is also a citizen of UK, but Richard Branson and Beckham have very little to do with each other. So what we do, and I will skim over this, is basically we trace paths from positives to positive destinations and from negatives to positive destinations. And then we define path features, and then the learning algorithm reads out meaningless red paths and retains the high signal green paths. So if I try to claim that two things belong to the same type in this graph, that must be because the green paths rather than some of the red paths. So this analysis feeds back into these tables. Okay, so now I'll talk a little bit about evaluations. So TMI does two things together. It tries to assign a type to the new previous entities, and it tries to find mentions of the new previous entities in the payload corpus P. So we don't talk about the typing too much because it turns out in typing it doesn't get much better than baseline. The place where it shows its strength is finding mentions of previous entities in the new payload corpus P. So the baseline there is 0, which purely uses that initial signal of affinity between the entry neighborhood and the mention. That's A0. And then there's this recent application from Zeng and others, which you call Z0, which uses some kind of semi-supervised scheme. I don't have time to go into detail. The second part of the talk is also there. So let's get that. So it has 3 experiments. So we took people from Wikipedia and Freebase. People is a very large set, and it's very difficult. Ambiguity. Much more difficult than to decide whether Apple is a tech company or it's a fruit, or whether jobs means employment or celebrity from Apple. So that's what we typically find in the literature. We didn't want to do that. We wanted to challenge ourselves much harder. So, and we picked a subset of people subtypes from Yago. So Yago is a entity and type catalog released from the Max Planck Institute in Germany. And it's modestly an acronym for yet another great ontology. So we use their type system for our work. So Wikipedia entities will call W, and the corresponding Wikipedia corpus will call CW. The nice part about using the Wikipedia corpus CW is that it's already tagged by humans. All sections are tagged. And that's why you find so many papers searching under the lamppost and using Wikipedia corpus, because there's no need to produce ground truth anymore. But again, that's not where we want to stop. We actually want to find out the performance of our algorithm over real web corpora. So we took this web crawl with 700 million pages done at CMU, which is called Web2. And we had the benefit of 20 professional editors from Yahoo who could judge the output of our algorithms versus that of other people's algorithms, like Z0 and A0. They were asked if a snippet annotation was correct or incorrect. It was too burdensome to tell them to find the correct entity from Freebase, because very often we talk with people who are unfamiliar to these editors. It's pretty difficult to go into Freebase and find out which of 200 John Smiths a particular page refers to. It's a lot of work. So therefore, we only tell them to judge post facto precision. So recall is pooled across different algorithms. And we also compared our data against a set called FSCC1 from Google. So it's COF annotations of the ClueWeb corpus. So coincidentally, it turned out that without talking to each other, Google and we were doing the same thing for about a year, and they were about to release their dataset, and came to our notice that they were releasing their dataset in 3 or 4 weeks. So I told my students, well, that's your hard deadline. We need to find some conference to send this work before 3 weeks, otherwise Google will release the dataset. But so we sent it in this paper, and naturally the reviewers said, now that the Google data is out, you need to compare yourself with Google. So we're kind of scared about that. And we'll see. So I'll maintain some suspense about where we landed up vis-a-vis Google's data. So here's some initial results. So the upper graph talks about Wikipedia with Wikipedia's corpus. So we could think of this as easy, in the sense that ground truth was given to us. And the lower graph is Freebase with ClueWeb2 about the payload corpus, which is a much harder problem. So what are these two charts? There are actually 2 y-axes. The x-axis is just a bunch of entities sorted in some reasonably looking order, so the graph turns out to be looking. And we confirm what people have suspected long back, which is John Smith is the most often used name in the cosmos. On the web, there's George Fisher, who is close. Of course, we're not writing all names. These are like already tens of thousands of names here. So we're only showing some prominent citizens of the world. And these are some of the most frequent entities. We also didn't pick only the most frequent or least frequent ones. So there's in the paper we described non-trivial sampling protocol, so that we are reasonably sure the numbers you see here are representative of what would happen if you unleashed TMI on the whole web. And that's difficult. So here are some things you should not do. You don't want to say, I want to deal with only a subset of types, because a lot of John Smith ambiguities might be between painter and farmer. And if you eliminate farmer from your type system, you may have resolved some ambiguities artificially. You don't want that. The second is, you need to complete snippet clusters. So if you pull up a snippet cluster with a John Smith, you need to bring in John Smith as an entity and then pull in snippets with aliases of John Smith. Unless you do this cluster completion, you are artificially chopping off a part of your entity cluster. Okay. So it's perfectly okay to experiment separately with Michael Jordan and John Smith because they don't have any overlap. You could throw out one and keep the other. But once you're committed to John Smith, you must solve the whole John Smith problem of the web. There is no subsetting that. Some earlier papers fudge that, so it's important not to do. And the second thing is, once you collect a whole bunch of John Smiths with different popularity in terms of web mentions, you need to do a stratified sample. So you're pulling in John Smith with different degrees of notoriety. You don't want to solve your problem only for the obscure John Smiths or only the famous John Smiths. You want to draw a representative sample of different notoriety scales. So that's completing the cluster. So what are the two y-axes? So ambiguity is the number of different people called John Marshall or Paul Smith and so on. So, and these are sorted by ambiguity. Of course, there is a whole bunch of people who appear only once as only one person in Wikipedia. So of course, on the real world, Paul W. Smith must have tremendous ambiguity. Inside Wikipedia, it turns out only one person is called Paul W. Smith. So as soon as you get down to one, inside Wikipedia you don't have a disambiguation problem anymore. So the interesting zone is 2 or beyond. Now, we're also constrained by completing the cluster. As you complete the cluster, you'll of course get unambiguous entities also. So we are forced to sample some unambiguous entities, but this shows that we also sampled a lot of ambiguous entities with up to 30-35 way ambiguity. So this spectrogram, if you will, should be compulsory to present in a paper to show that I wasn't only disambiguating easy things, I was also disambiguating difficult things. Now this y-axis and this x-axis are totally different on the web. So here, lack of ambiguity happens much further on, where you have crazy names like George Westcott Fisher, which may be a character of a PG would have something. So whereas things like Kevin Bacon and Tom Clark, this y-axis is actually on a much bigger scale that's being hidden here. And the number of snippets I collect from the web is now like in the thousands. So 30,000 snippets with Darian Graham Smith. Whereas the y-axis here is purely in the thousands. So the number of snippets we collect from the real web corpus is 3 orders of magnitude or 2 orders of magnitude larger. So here are the results. There's another consideration, which is on the Wikipedia corpus, we know that every qualified snippet does mention to an entity other than null or bottom or any. Whereas on the web corpus, you have to allow nulls because there are lots of snippets which don't mention to any known entities in your catalog. So null not allowed, null allowed. And here, so we plot two things. One is 0-1 accuracy, whether the snippet was correct or not. And this is a pooled F1, which is this harmonic mean of recall and precision. The first thing to observe is that PMI, which is the blue bars, we beat both the annotation baseline in the previous part of the talk as well as the Z0, the Zeng system, reasonably well. In fact, the gap is pronounced especially at the low end of degree. So this is degree in the knowledge graph in previous. So for entities which are very new, the degrees are low. And that's where we gain the most accuracy compared to the existing system. And that's what we set out to do. So this is on Wikipedia itself. Right? When we go to the web corpus, we find even bigger gains. So, and now we dropped the Zeng system because its accuracy was lagging far behind, and we only looked at A0, our previous system. And so you see that we have a little bit of a lowered recall, so we are more selective in what we decide to annotate. But in exchange, our 0-1 accuracy and our precision and F1 are far better than the baseline annotator. The other important thing that should spring to your mind, if not now in a few minutes, is that, well, when we did this cluster expansion on the real web corpus, we might have started off with obscure entities in Freebase, but we might actually have walked into entities which were in Wikipedia itself. Are we gaining this accuracy purely because of well-known entities which are competitors to less-known entities? Or are we also good in the entities which are in Freebase and not in Wikipedia? So it turns out that TMI wins over A0 in both categories, but of course the absolute accuracy in the Wikipedia categories is larger because I have more training data. But we also win in the obscure entities which are not in Wikipedia. And again, we show a plot, a breakdown of the results of these aggregate numbers by buckets, depending on their degree in the previous graph. And again, for the very low degree nodes, we gain more accuracy compared to the baseline. If the entity is very well linked in Freebase, it might already be in Wikipedia, and then you have a solid evidence, and baseline algorithms might do fine in that regime. So here's the comparison with Google. So FSCC1 is Google. So in about 22% of the cases, both of us got it right and none of us said no. In 40% of the cases, Google backed off and we did not, and we did okay. And in 23% of the cases, Google said no, and we made a commitment and we got it wrong. So it means that Google was being very conservative about precision and losing a lot of recall. Whereas we were a little worse in precision, but in the balance, our algorithm gets both better recall and precision. So the summary of part 1 is that the catalog is always work in progress. And so you need to maintain this mention linkages between the corpus and the catalog as the catalog evolves. And so it presented techniques for first doing the head entities by the collective labeling techniques. And then second is to extend from the head entities to the tail entities by this tripartite assignment model. So it seems you can raise recall without sacrificing precision. And this dramatically boosts tail entity annotation accuracy. And our entire dataset has been made available publicly at that URL. So now we come to the second part, which is, well, so since we have all this machinery to annotate entities and relations, entities on the web corpus, how do you use it for answering queries? So if you have any questions for the first part, this is a good time to ask. Yeah. Yeah. Yeah, so we're very glad that the numbers came out this way. But they move fast. So now let's talk about search, which is perhaps the biggest application of doing all this. So in 2012, the web conference, Microsoft did a study where they showed that at least 14% of web queries refer to a category or a type, possibly with defined. And another 14% mention entities with defined. And 29% mention an entity on its own. So these are often navigational queries. So you say American Airlines, and clearly you want to navigate to the home page of American Airlines, maybe to book a ticket. Or entity plus definer may be things like iPad price or iPhone battery life. That's entity plus definer. Sometimes entity plus definer queries themselves have types in it. Like when you say iPad price, you're looking for a price, that's the text. And these are things with explicit categories. So I'll give some examples of these kinds of queries. So this is pretty huge. It's a huge slice of queries. And if you want to take away one message from the second and last part of this talk, it's this, that different tokens in a telegraphic query have very, very different purposes. And regarding them as just words in a flat space with only rarity or IDF to do your scoring doesn't work anymore. Different tokens have to be interpreted to different purposes, and those different purposes will lead to different scoring mechanisms altogether. So here's a paper from Microsoft in 2009 which talked about how different tokens in the query could refer to either the entity or something you intend to do about or with the entity. So we're talking about very short queries, different from entity disambiguation in longer text-like documents. So it's a harder problem. And they define three random variables of interest in the background. One is the type of entity. So, and they're restricted to commerce queries for ease of experimentation. So the type of the entity could be book, movie, game, song, organization. And entities could be ambiguous. You might say Harry Potter in the query, but it may not be a book, it may be a movie, or it may be a video game. Or you might say YMCA, and YMCA may be the organization, or it may be an album by a music man. So, and then the only way to figure out what you're trying to do with this entity is to look at left and right context terms, which they call N1 and N2. If you say Harry Potter DVD, then it narrows down, maybe it doesn't, maybe there's a DVD with a video game, but if you say YMCA DVD, it's unlikely you're talking about the organization. Whereas if you say YMCA address, you're probably looking for the local YMCA organization. So the context expresses intent, right? May also disambiguate alias entities of different types. So here are some examples of entity action queries. So you say watch Gladiator online. So the entity is Gladiator and you want to watch it online. Or you say 12 Angry Men characters. You're looking for the characters in the movie called 12 Angry Men. Now of course the unfortunate thing is that the query as it enters the search engine is not conveniently color-coded. So the search engine has to first take apart the query into red and blue tokens and then decide how to deal with each of them separately. Now, unless you already covered this yesterday, so warn me if you have. So in standard information retrieval, there's this notion of a generative ranking model, or ranking or scoring documents using a generative language model. Also called probabilistic retrieval or probabilistic language models. Have you gone through this already?
Yes.
So then one slide will suffice. So suppose I have a query and a bunch of response items I'd like to rank. This may be pages in case of standard IR, or it could be entities in the current situation. So for every item U that you want to score or rank, you create some sort of probabilistic model MU that generates the query backwards. This is the opposite way of thinking about it. And then the probability of generating the query given MU is a scoring signal to rank among different competing U's. Now note that the model goes from the response item back to the query. The search engine itself has to reverse the process through Bayes rule or things like that. So in case of the Microsoft paper, the generative process gets more complicated because of the involvement of entities and types. It's not just a document language model. So the joint probability of the entity, the context, and the type of the entity is the probability of the entity times the probability of the type given the entity times the probability of the context given the entity and the type. And in the query, you only see the words and the N. You see the mention of E and the context of it. You don't see the type at all. So the hidden process is that the user has a magic entity in mind, and E is described as a possibly ambiguous set of tokens in the query. Then you secretly choose a type for the entity. And then, often mentioning the type completely disambiguates the entity. So you say Harry Potter movie, and movie is an explicitly defined type. But movie may not be described explicitly. You might actually depend on N to define the type of the entity. It's a little unclear why you want to choose the entity first and then its type. You might instead choose the type and then the entity. So this is a little unclear from their paper. But the third step is clear. So what they assume is that this is an approximation. Once I choose the type, The type alone decides the context. The specific entity does not decide the context. And then query interpretation means that given a query, you want to argmax over En and T of the probability of En and T times the probability of generating the query given En. So that gives you the hidden entity and type given the query, and then you can process your query as you wish. So here's a pictorial interpretation which may make it easier to understand. There's a certain distribution from which your target or secret entity is sampled. That's the site. And then for every entity, there is a distribution over types. So if you have Harry Potter, then there could be different types like book or movie or game. And for every type, there's a distribution over intent of what you want to do with it, which dictates the whole query. So for each query, you first sample an entity, which you don't show, of course. And then for twice, for the left and right context, you sample the type. Why the type is sampled twice is unclear from the paper. And then you generate the context words given the type. So that's the plate diagram of generating the query. So this gives us some impression of where web search has come from the last 10 years. I mean, in the beginning there was TF, IDF, and vector space. And apart from IDF and TF, all words in the query were notionally at par with each other. But now queries are modeled in the system as being generated from processes like these, and then different parts of the query are used differently in doing the query execution. So T may be unavailable in training data, so you might need to use something like EM to fill in the missing data. So I'll cut this short.